Hi, everyone. My name is Jack. I am a postdoc at the Allen Institute for AI, and I'm super excited today to get the chance to talk with you about at least two conceptions of visual textual grounding. I'll break that down a little bit during the talk. Um, I first must apologize for not being able to be there with you in person. I got sick this week, which was unfortunate, but I am super happy to be recording this for you in the hopes that maybe we can talk in person after if you have questions. I should also say this actually isn't the only opportunity I've had to speak at Pitt before. So in simpler times, I visited Pitt and gave a talk in the Digital Humanities Research Group there. And so I've seen the Cathedral of Learning, and while I'm sad to not be visiting again, it isn't such a big loss for me, I suppose, because I've seen your wonderful campus already. I've seen the Cathedral of Learning, it's beautiful. But yeah, so let's jump right in. Before I talk about these two conceptions of visual textual grounding, I want to motivate this field more broadly. So why might you care about learning visual textual connections in the first place from machine learning or artificial intelligence perspective? Well, I think there's a compelling case to be made that many really interesting AI tasks simply just require learning these connections. One example is alt text generation. So this is quite useful for blind and low vision users of the web. So algorithms here take in the image as input and automatically generate alt text. Many images on the web just simply don't have this alt text right now. And if we could automate that process, the web would become more accessible. Similarly, there's interesting applications in human-robot interaction. In the future, we'd like to be able to talk to robots using a natural language rather than some formal logical language. And we'd like robots to be able to map our language onto the physical world, which they normally interpret via cameras. So you need to understand visual textual connections for this task. And similarly, there's some interesting applications in web video parsing. It turns out that people really like in instructional videos when not only the video is displayed, but also a timeline of sub-goals is displayed alongside it. So this improves user experiences drastically. And to generate, a timeline like this at scale, you would probably need some automated tool to do this. Good. So those are three practical reasons why you might care about learning visual textual connections. But if you're more interested in just AI, like grand goals of AI, like artificial general intelligence or something, these sorts of cross-modal reasoning problems, there's tons of them out there, but they're quite hard. So these are easy for humans to do, but really hard for computers to do. So here's an example from Zellers et al. And it's a visual question answering task. So there's a question and an image, and the algorithm must reason about connections between these two modalities to answer this question. So why is person 4 pointing at person 1? Back in the days when we used to go to restaurants, maybe you went to one and you might be able to answer this question. Why is person 4 pointing at person 1? Well, it's because person 1 probably ordered pancakes. And that's quite easy for us to determine, but if you break down the reasoning that's required, it's actually pretty darn complicated, right? So we have to parse the scene, we have to parse the relationship between these people, we have to parse the question and map all of these into a shared space somehow where we, bridge the modalities and then answer the question. So there's a lot that goes into even simple cross-modal inferences, and humans aren't quite there yet. There's a huge gap on this task between computer and human performance. But beyond AI, there's also other reasons to care about visual textual reasoning. It turns out that cognitive psychologists have been studying different connections between language and perceptions for quite some time now. I definitely don't have time to give a full overview, but it seems to be an intrinsic piece of human intelligence that we're able to reason across modalities pretty efficiently. And certainly visual textual reasoning underlies complex phenomenon like the symbol grounding problem, for example. Good. So if you needed yet another reason to care about this, it turns out that the internet these days is very, very multimodal. So perhaps if you're interested in studying communication online, as many people are, you should be interested in image text reasoning. This is because rarely a social media post is made these days without a visual component. And this is different than, say, back in 2007. you can see this plot here from Reddit where the proportion of news articles is falling relative to the proportion of image posts. And so we're increasingly becoming a multimodally communicative online world. If you scroll on your Facebook, for example, if you have one, you might notice that everyone posts images along with their text. And this might seem a little bit depressing, so maybe we're posting cat images instead of reading news articles, but semioticians have long posited that multimodal communication is intrinsic to how we communicate. So for, a very long time prior to the printed word, we mostly relied on face-to-face communication. And, there's a reason why I'm recording this talk right now. I'm using my hands to talk, I'm using my prosody to talk. And there's lots of intrinsic aspects of human communication that at least semioticians think are quite important. Good. So how do people actually use images and text to communicate on the web? Martian Domus White in 2003 asked this question, and their answer was that it depends. So image and text, when used in conjunction to communicate a message, can take on any number of different patterns. So images can be used to reiterate text, or text can be used to organize images, and so on. And so there's a huge diversity of different ways that people can use images and text to communicate. So I won't dive into this particular taxonomy too deeply, but I am a fan of the idea that there's a typology underlying a lot of these multimodal communications. Cool. So another quick aside, if again, just pitching web data because that's something I'm quite interested in. If you were to want to create a machine learning model that performed really well at any given task, and you only had 1 week to do it, I would recommend not trying to design a very smart algorithm to do this. I would recommend just downloading a bunch of web data. So if you download a lot of this image text web data and pre-train a model on it, it turns out this is an unreasonably effective way to achieve good performance on different machine learning and artificial intelligence benchmarks. So this holds for image and text tasks, for video and text tasks, and even really for unimodal tasks that don't span the modalities. The pattern persists. You have a task, you want to solve it, you pre-train using a giant web corpus of unlabeled data. So even if you're not interested in image text communication from the perspective of, I don't know, cognitive science or semiotics or anything like that, you should be interested in it if you're a machine learning person, because these are the benchmarks you're going to have to contend with, when you're doing your tasks. So this is a very good way to get high performance on different tasks. Good. So I hope I've given a quick pitch, or a convincing quick pitch, of why you might be interested in image and text data to begin with. And the rest of today is going to focus on two conceptions of visual textual grounding. And I've shown these three examples here to sort of highlight the diversity in different data sets that might be out there. So there's lots of different ways that images can co-occur with text. This first example on the left is from Microsoft Cocoa. This is a data set of images and literal captions that will come up. So this is surely one way that images and text can coexist. Is this sentence grounded in this image? Most people would probably say yes in the community, but we'll dive a little bit deeper into what that means in a second. We have slightly more ambiguous examples. So here's an example from one of our previous papers where someone has posted cat images and cat captions to Reddit. And you can see that, you have an image of two cats crossing necks, and then you have this clever caption. It's an idiom, the grass is always greener. And this is one way, another, non-literal way that images and text can co-occur. And finally, just on this slide, there's tons more out there. These are just three sort of examples. Folks you may recognize have looked at different websites that are instructional in nature. And so here we have, someone cooking, I guess, ravioli or something like this. And there are images to go along with these recipe steps, and also there are texts. So the co-occurrence of image and text on Instructables is very task-oriented. So lots of different ways. I just wanted to highlight a quick, give you a concrete touching point for the great diversity of different modes of communication that images and text enjoy on the internet. So yeah, what is going on here? The first idea we're going to talk about is from unsupervised learning. And the idea is you don't have any labels. You just have a bunch of people, say, talking online or posting things, or really just any images and text co-occurring. And the core idea here is that maybe what it means to be visually textually grounded is if a computer can identify a consistent cross-modal pattern in this co-occurrence data. So if, the word cat always co-occurs with the set of pixels that happens to look, like a cat face, perhaps that's what visual textual grounding is. And this is a nice idea. The best thing about it, I think, is that you don't have to collect a bunch of labeled data. Good. And so I'm going to talk about two of our projects that build upon this notion of groundedness. The first one deals with static images co-occurring with text, and the second one deals with video co-occurring with automatic speech recognition tokens. These are things that YouTube automatically generates if there is a speaker in the video. It'll transcribe the audio. But yeah, so we'll dive into the static images project first. So again, one problem this field is facing is that a lot of our data sets really focus only on literal objects and actions. And so you can see that, most people would say this image and caption is grounded. And this is a fairly artificial setting, right? So I've shown you other examples of cases where people are using images and text to communicate in a more diverse fashion than just like a literal dry description. Like if your friend posted this on Facebook, you might message them and make sure that everything was okay. Like this is make sure they weren't hacked or something. This is very robotic. And yeah, so this is robotic on purpose. It turns out that this data set was specifically constructed to be inhuman. So the annotators were told to not describe what a person might say. And this is, something that we would expect to find grounding patterns in, but there's probably something more going on, especially with more diverse data sets. Hill and Cahornan noted that a lot of our multimodal learning algorithms really only work great when they're dealing with data sets like Microsoft Cocoa, where everything is very concrete. And so the goal of this particular project is to quantify how visually concrete different concepts are in a wide variety of different data sets. And again, connecting back to this grounding idea, the idea is that some concepts may be more concrete and visually grounded when compared to concepts that aren't. So perhaps dog maybe is a very concrete visual concept versus beautiful, which may be more spread out. There's lots of work on this sort of operational notion in static images prior to our work, but we like our algorithm because it's fast. It can generalize to things that aren't discrete words. So it generalizes to, topics from latent Dirichlet allocation, if that means anything to you. And we also ran our algorithm on more data sets when compared to prior work, which we feel is an important contribution to show that data sets of this form really vary. Good. So let's get started. How do we compute the concreteness of a different concept in these data sets? So we assume we're given image text co-occurrences. So perhaps these are from Wikipedia, the images in Wikipedia articles and the text surrounding them. Perhaps these are from, Flickr posts. Pretty much any setting where you have images and text naturally generating co-occurrence data, you can use this algorithm. Here I've given a toy example of, a bunch of images of cats, and we'll say they're associated with these cat sentences in our corpus. And here are some images of beautiful, and you can see that these are associated with these beautiful sentences. Now, you can immediately see there's a difference between these two clusters of images, right? So the cat images tend to picture, relatively homogeneous set of objects. It's usually a cat and maybe some other stuff. In contrast, beautiful, lots of things can be beautiful. So cakes can be beautiful, babies can be beautiful, peacocks can be beautiful, sunsets, so on. So you can see that at least in terms of the objects, there's a huge variance here. So beautiful images are highly varied, cat images not so much. And it's exactly this variance that we're trying to capture using our algorithm. So how does this algorithm work? Well, you take all of the images in your corpus and you pass them through a feature extractor. You can use really anything you want. So there's no sort of universally accepted best image representation. In this work, we used what is common, which is a pre-trained convolutional neural network for object detection. But you can sub in anything you want. And so you can see that something like this might happen. So you take your images, you pass them through your feature extractor, you get some vectors, and these vectors might cluster in the resulting image feature space. So I sort of suggestively clustered, the cat images quite close together, whereas I've put the beautiful images sort of evenly spread throughout the space. And indeed, this is actually what happens in practice. And it's exactly this clusteredness that we're going to be quantifying. So the idea is more concrete things will cluster more tightly in this image feature space compared to less concrete things that will spread out more. Now, I won't get into the exact math of our particular algorithm. If you want to see it, you can check out the archive version of the paper. Actually, the ACL version has a typo in this equation, but there's also an implementation out there on GitHub which works. But so I won't get into the details here of measuring clusteredness, but I will draw this close connection our algorithm has to geospatial statistics. So geospatial statisticians are often interested in the clusteredness of different statistics over real-world maps. This example is the clusteredness of cancer rates in Long Island. And so, if you found some statistically significant correlation between spatial distribution of people and cancer rates, you might, plausibly think that, like maybe some of these regions like have contaminants that are contributing to cancer rates. And so, there's a statistic called the LISA statistic, and it measures clusteredness. And our approach can be viewed as a high-dimensional extension of this LISA statistic. Good. So enough talk. Let's see some results. So we ran this on Microsoft Cocoa, this literal image caption dataset. And what pops out is the following. According to our algorithm, these are the most concrete words in Microsoft Cocoa. So it turns out walk, the cooking instrument, is the most concrete visual concept in, Microsoft Cocoa, according to our scoring. So that makes sense. So walks, they're always in a kitchen, they're always on a stove usually, sometimes there's food in them, makes sense. Some of these make a lot of sense, like hummingbird, okay, sure. But maybe some of these don't make so much sense. So think about the word delta, for example. How could delta possibly be visually concrete? Like it means so many different things. So it's very polysemous. Delta can mean, like a river delta. Delta can mean a change in something. Lots of meanings for delta. But it turns out in the Microsoft Cocoa dataset, delta is always airplanes. I went through and checked. Every time delta is mentioned, it's an airplane. So this is why it's very visually concrete. And there's other weird ones in here. So unripe, for example, any unripe can be, fruit, but it can also be a, metaphor for something. The sun was unripe. I don't know who would say that, but I don't know. But it turns out, in Microsoft Cocoa, it's like always bananas. Not strictly always, I did check, but most of the time, 99% of the time, unripe is bananas. And thus, in this data set, it's very visually concrete. Good. So we're starting to see some effects of dataset specificity. Our algorithm is surfacing a mix of things that a priori you might think are visually concrete, and also some things that just happen to be visually concrete according to this particular data distribution. And we think that's kind of cool, right? So some of these differences between datasets can be highlighted by looking at concreteness scores. So London, for example, is a very concrete word in the Microsoft Cocoa dataset. This is because of how it was constructed. This is, a data set where people on MTurk wrote captions about images after the fact. And so you're not going to say the word London unless, the image presented to you is just screaming London, like has to be double-decker buses, Big Ben, the London Eye. It's hard to tell if any given image is, just happens to be taken in London unless it's screaming at you, London. This is in contrast to a Flickr data set where people use London as a geotag. So we see some images here that you might not be able to tell just from the image are taken in London, but nonetheless are tagged with this geotag. And so as a result, the concreteness of London falls precipitously in the Flickr data set. So we're surfacing some interesting data set specific correlations here. Good. So to give you a fuller picture of the Microsoft Cocoa results, here are some somewhat concrete word types, and here are some not concrete word types. We did some checks to make sure that we weren't simply correlating with frequency. We did some human evaluation to make sure that people's judgments of concreteness align with these rankings. It all checks out. We're not just doing frequency, and yes, we align with humans. So what are some implications for machine learning? It turns out that kind of unsurprisingly, more concrete things are easier for image text algorithms to learn about. I won't get into the details of the experiments here, but here are plots for 4 different data sets. The x-axis is concreteness, so as you go right, you become more like cat, and as you go left, you become, more like beautiful, which is harder to concretely visualize. And the lines here represent how well different algorithms can learn the connections between images and text in this setting. And you can see as we go right, so the more concrete things are, the easier they are to learn. So this is kind of unsurprising. A computer vision algorithm does better at learning what a cat looks like than it does learning what beautiful looks like. So, I mean, it's not unexpected, but it is a little bit sad. This suggests that maybe some concepts, our computer vision algorithms just simply won't ever be able to understand. And this is kind of bad news. But some good news is that actually, even if you go all the way to the left of these plots, even for the most, visually abstract concepts, we're getting above random accuracy. So I haven't told you what the y-axis really is, and I won't, but random guessing is at 0. And in all of our data sets, we're above 0. So maybe there is some hope. And a hopeful open question is, maybe this sort of problem can simply be solved by more unsupervised data. This is a pattern that we're seeing, again and again, where people are downloading a bunch of data, training some unsupervised algorithm that learns representations on that data, and then using those for downstream tasks. So maybe the shape of these curves, for however sad it may be, maybe we can just shift them all up by just downloading more data. And this is an avenue that myself and a lot of others are actively working on, is just like, can we overcome this problem just with scale? It's an open question, so we'll see. So here are some results for LDA topics. So if LDA doesn't mean anything to you, just think instead of unigram types, which are discrete, like either a word is present or not, we now instead have distributions of words in different topics. So the hockey topic might contain ice, puck, player, body check, words like that. And indeed, our algorithm generalizes to this continuous concept setting, and it makes sense. So on Wikipedia, ice hockey is very visually concrete, usually because it's some dude with a hockey stick over a white background. There are some like less concrete topics, like ironically, our least visually concrete topic was linguistics. So linguistics can be, old dudes who do linguistics. Linguistics can be, maps of, like different languages across space and time and so on. So this is just an example of running our algorithm on Wikipedia. I'd like to shift gears a little bit to some recent work that takes the same concept of quantifying the predictability of different concepts, and instead of applying it to static images, applies it to web videos. The sort of data we're going to be looking at are web videos alongside their transcriptions. So here's a cooking video, and the speaker in that video might be saying something like, first, we'll prepare the ingredients. Second, we'll put 3 ounces of lemon zest in a bowl, and so on. And the idea here is that we can leverage this data to learn connections between these 2 modalities by aligning video clips to their corresponding narrations. Now, this is a popular idea, and we're not the first people to think of it, obviously. But much of the prior work in this area has focused more or less exclusively on instructional videos. So a priori, we expect instructional videos to be very visually textually grounded. So we expect, speakers in instructional videos to make reference to objects and actions quite readily. So maybe I'm, telling you how to make a latte, and I have a mug, and I might be like, first you grab the mug, and the computer vision algorithm can see the mug, and it can learn what a mug looks like. And this is nice and enables a lot of really interesting applications, but it turns out that most of the web isn't instructional videos. There's all sorts of videos on the web, as I'm sure many are aware. And the big question we were pondering in this work is, can these same approaches that have been so successful on visual textual grounding for instructional videos be applied to this much broader swath of videos? So our goal is to explore this operational notion of grounding across YouTube. And here's our game plan. We're going to first gather a more diverse corpus of YouTube videos compared to prior work. Second, we're going to train a model on that corpus that aligns video clips with speech recognition tokens. And finally, we're going to conduct an error analysis. So which types of videos are very predictable and which types are not. So if you think, like instructional videos, probably you can learn visual textual associations between pretty readily, but maybe something like a video game commentary, you might not be able to. So if you have someone playing some video game and then they're, maybe a YouTube personality and they're talking about their vacation while they play Call of Duty or something like that, probably you can't learn any visual textual association in that case because there just like isn't one semantically. But nonetheless, we want to explore this operationally. So we collected a data set of different videos paired with their speech recognition transcripts. And the corpus we examine is a subset of the YouTube 8 million corpus. Here's a random example from it. This is profiling a athlete, and there is a narration. And so we get the narration and we get the video frames. We're looking here at our training set is something like 600,000 plus videos. And then our development set is something like 130,000. So quite a few videos. And they range quite broadly in different categories. So in the paper, we argue that the YouTube 8 million corpus is much more diverse than other instructional video corpora in the sense that it contains fewer instructional videos. So if our goal is to see if we can do visual textual grounding beyond like cooking videos, we first need to prove that our actual corpus contains things that aren't just cooking videos. And so we collected annotations, human annotations for 6,000 videos. Sorry, this shouldn't say 18K judgments per video. There's 3 judgments per video, 18K judgments total over 6,000 videos. And the result is that in YouTube 8 million, around, a quarter of videos are instructional, but 3/4 are not. And we'll be releasing this corpus soon. If you want to train a model that predicts, whether a video is instructional or not, that would be pretty cool. If you're interested in this sort of thing. Good. So what are we actually going to be doing with our corpus now that we have quantified how non-instructional it is relative to other corpora? Other corpora, it's usually upwards of 3/4 of the videos are instructional. So here's what we're going to be doing. We're going to be doing a link prediction task. So we're going to be putting on our, network prediction, our link prediction hats from social network analysis, and we're going to be treating each video segment as a node in a graph, a bipartite graph. The other half of the graph are going to be ASR segments, and we're going to be doing link prediction, and the true edges are going to be the temporally corresponding edges here pictured in green. These are associations that we'd like to score highly. The scoring function here is S. And in contrast, relative to the true edges, we'd like to, be downweighting the score of these fake edges, which are simply temporally mismatched segments. So if you're familiar with the link prediction literature, the particular metric we're going to be using for evaluation is called AUC. I've given a quick formula for it here. Basically, you have some scoring function and you want to know how well it reconstructs this graph. You loop over all of the true edges, and you count how many times you score a true edge more highly than a fake edge. And you do this for all possible pairings. And so higher scores are better, 50% is random. So how are we actually going to compute this scoring function? We're going to use neural networks. It's 2020, or I guess when we were doing this, it was 2019. Let's use neural networks. So we're going to take our video frames. We're going to extract 2D convolutional features. These are like ImageNet object detection features. We're also going to be extracting 3D convolution features, which if you haven't seen before, if you haven't worked with videos, essentially they're, in addition to the pixel X, pixel Y dimensions of our normal convolutions, we're also going to be doing like a temporal dimension. So our convolutional filters are cubes now instead of squares. So cool. We're going to use both of these types of features. There's some work from computer vision that says these might capture different things. We'll just use them both and not worry about it. And then to represent a segment of video, we'll extract these types of features from each frame and then max pool. So it turns out max pooling is actually really hard baseline to beat. You might think the order of these things matters. We tried all sorts of stuff. Max pooling, for however many downsides it has, is actually really good. So we max pool. Good. So similarly, on the text side, we're going to take our ASR tokens. So these are detected automatically by YouTube and generated. And then we're going to max pool a feature vector for each one. Again, this hurts me as an NLP person to just max pool over the length of a sentence, but nonetheless, it works really well in practice. So just cringe with me for one moment and then max pool going forward. Just give it a shot. It actually works really well, which is kind of sad, but anyway. Good. So that's how we represent our video features and our text features. And then we simply compute the cosine similarity between those two. And again, we're trying to compute a temporal alignment where the temporally corresponding ASR and the temporally corresponding video are scored more highly than temporally mismatched ones. And out pops from all of this a single metric for each video representing how well the algorithm can make this temporal alignment. So yeah, these are dev set results. So this isn't simply memorization. Unless there are duplicates, which there might well be in YouTube 8 million, but you can look at their paper for more details. There's not that many duplicates if there are any. So we're generalizing here, at least statistically. Cool. So which are the categories that we can ground very well under this operational notion? Well, it turns out, there's a lot of videos out there and a lot of types of videos you can do this for. So there are vehicles. So it turns out like people, I've discovered so many types of YouTube videos from this project. So people, I'm not a car person, maybe other people are car people, but like there's a huge segment of YouTube where people just get their webcam and they like go around every little corner of like their car and they're like, this is the wheel, this is the back seat, this is the I don't even know what cars have. I just write in them. But anywho, so that sort of setting, it turns out you can ground very well. Kind of unsurprising, but people haven't examined it before and it pops out of our analysis. There's also other ones. So there's like tech reviews, there's appliances. So people really do appliance reviews. This is my stove. Here's the inside. Here's, the cooking surface and so on. And, these categories sound silly, but really like there are entire YouTube channels that are based on this and, millions of views. Like if we could develop tools for these scenarios, this could really deliver a lot of value for both the producers and the consumers of these videos. Is it really any more silly than looking at, makeup tutorials as in prior work? I'm not trying to downplay the importance of makeup tutorials. I think they're great too, but there's lots of different categories on YouTube and we should treat them with respect, even if, I'm not a car person and I think it's a little bit silly. Good. So here are some individual categories. Again, 50% is random guessing. 100% is, perfect prediction, which we wouldn't expect to be possible. Here are some different meta categories. So it turns out, the blue here is the overall distribution. So we're getting, above random for most videos, but usually we're, in a, between 50 and 60 AUC. Games turn out to be a hard category. Beauty and fitness, it's relatively high. Food and drink is also relatively high. So we think this framework allows us to, discover all sorts of different categories that have yet to be explored in this visual textual grounding world. But why can we actually do this, right? So I've shown you some meta results. Like I've told you that, the category of car walkthroughs, you can do visual textual grounding on. But what's actually going on here? So we did a few case studies of different categories. In particular, we looked at action figure, which has high groundability, and then we looked at Call of Duty, which has low groundability. We controlled for factors like segment timing and the number of tokens in different segments. So you might think that, segments in the middle of the video might be harder than at the beginning and the end because it's quite easy to visually identify like intro cards and outro cards. Turns out, yes, that is the case. You might also think that simply having more tokens in a given segment is easier. Turns out for action figures, yes. For Call of Duty, no. But even after controlling for all of these non-content factors, there still are, semantic content factors that are predictive of how well a given segment can be grounded. So for action figure, these are things like knee, joint, shoulder. Presumably, these are words people are saying as they're going through their action figures and pointing at different things. And so these are the words that are predictive of groundability. For Call of Duty, again, these are videos of people playing a first-person shooter and then talking about stuff. Not so easy. There aren't so many interpretable patterns. In both cases, however, we do see this sort of I don't want to call it an artifact, but a pattern that probably isn't what we think of when we think of visual textual grounding. It's like you can identify intro cards really well, and people in the introduction of videos often say, "Hi, welcome to my video," or something slightly less artificial than that. But it turns out you can ground, beginning and ending language quite easily. And this is a downside of an unsupervised way of quantifying grounding, right? Because you have to just rely on co-occurrence data if you don't want to label anything. So you get things like this. So by this definition, intro language for YouTube videos is grounded, which is, a little bit awkward, but at least it's discovering some interesting patterns. So I'm not saying this is the best notion of groundedness, but it is one of the, I guess, best ones we have out there, especially for unlabeled data. Cool. So those were just a quick overview of two of our projects. The camera ready for the video one will be coming out soon. So if you're interested in that, I can send that to you. But I'm actually going to switch gears from this unsupervised learning setting, wherein we're talking about quantifying groundedness from co-occurrences, to a setting, to a supervised learning setting. And the idea here is that there are some functions that are grounded functions, and there are some functions that are not grounded functions. And we're going to do our best to make this distinction. So if the function cannot decompose into unimodal components, then it requires learning grounding. So again, I motivated this whole talk by the idea that learning visual textual connections is, what we all think of when we're thinking about visual textual grounding. And yet there are lots of tasks out there that can be solved, without incorporating any meaningful connections. And the point of this work is to put a number to that and give an algorithm for diagnosing this. Cool. So like I mentioned, here is our setting. Our setting is going to be mostly classification, but we think the setting can generalize beyond this. We focused on classification just for this first paper because people like classification. I like classification. Anyway, so we're going to be having textual and visual inputs, T and V. Again, here is our friendly cat example back where we have a good caption on a cat image. And then we're going to be trying to learn some target function F that takes in both the text and the image. And we're going to be making some prediction for these inputs. So this is a very basic image text classification setup. And there's lots of problems that fit within this paradigm. So the Microsoft Cocoa setting, the task that people often do is trying to retrieve a set of captions for an input image. So given just the image of someone playing baseball, you might want to retrieve all of the captions that could plausibly describe this. And that can be framed in this particular framework. So you take in your text and you take in your image and you want to produce a prediction of how likely they are to correspond in a literal sense. So retrieval models fall under this framework. Another thing that falls under this framework is some work that we did on popularity prediction. So I haven't told you the point of this cat and caption pairing, but it turns out the task we were interested in at the time was doing popularity prediction. So we really wanted to see how popular, if we could predict the popularity dynamics on Reddit. And finally, people might annotate these with different taxonomies of interest. So discourse relations is one great example where you have images and text together and you have a set of higher level, I guess, discourse relations that you would like to classify these pairings according to. But really, there's so many different tasks that have this form. So if you've looked at visual question answering before, you have a question and you have, an image, and then you have to make a prediction of the answer to that image. It turns out that state-of-the-art approaches for visual question answering these days frame that task as a classification problem. So they don't generate the answer. They actually pick the answer among something like 3,000 candidates. There's so many, there's visual entailment that has this form. A lot of different problems have exactly this form. Good. So how are these studies generally conducted? Well, the first step that people generally undertake when they're looking at doing image text classification is they identify some phenomenon of interest. I'm going to use our example as a running example just because I think our study, it has a lot of cool parts to it, but it also has, I think, a lot of pieces that in retrospect, I think could be done better. So I'm going to be picking on beginning grad student me. This is something that I would only recommend doing after you're older. So anywho, so the first thing that we did, or a lot of people do, is identify a phenomenon of interest. In our case, we were interested in popularity prediction. Next, people generally collect and label a data set related to that phenomenon. So in our case, we went out to Reddit and we collected a bunch of very popular posts and a bunch of very unpopular posts. Other people might label things. Other people might, go download tweets and so on. Third step in this pipeline is you train some prediction models. So maybe you train an image-only model, maybe you train a text-only model, maybe you train some complicated image-text combining model, and you compare their prediction performance according to your label set. And finally, usually these papers, including my own, conduct some mix of qualitative and quantitative error analysis to make the case that there's something interesting going on with these models. And that something interesting going on varies depending on the study, and not every study that does image and text stuff makes claims of this form. But usually what happens is someone will put out a cross-modal attention map where you have like images interacting with the text, and they argue that the model qualitatively is doing something reasonable. So this is generally how these studies work, and I think this is a pretty cool pattern. Like I've worked in this area for a while, and like I've written studies like this. I think it generally it's been working for us, but let's see if we can do a little bit better. And in particular, the methodological change that we propose deals with both model comparison and qualitative analyses. And in particular, the hypothesis that people oftentimes point to in justifying the efficacy of their different image text prediction tasks is that their models have learned visual textual connections. So again, I said earlier that visual textual grounding was all about learning connections between images and text. And this is a claim, this is a point that's returned to in a lot of these studies. So including my own, again, trying to harp on myself, but I think here's a quote from us. We wondered if the visual and textual interacted, sometimes, reinforcing and sometimes counteracting the influence of each modality individually. There's this theory from semiotics called meaning multiplication. The idea is that if you co-deploy images and text together, they can create new semantics by virtue of their, sophisticated cross-modal interactions. Here's an example. There's all sorts of examples of people, saying that it's super important that we're learning visual and textual connections for these classification tasks. And to operationalize this a little bit, we're going to adopt some framework from statistics. And the idea here is that we're going to draw a distinction between multimodally additive models and multimodally interactive models. So a multimodally additive model is one that cannot incorporate visual textual interactions at all. Stated differently, this is equivalent to the class of models that can be expressed as an ensemble of a textual predictor and a visual predictor. So this is like if you went out to a visual question answering task and then trained a language-only model that predicted the answer just based on the question, and next, you trained a visual-only model, which again predicted the answer just based on the image, and then you took an ensemble of these two very naive models. And in theory, it shouldn't really be possible to answer visual question answering questions without looking at both the image and the text and their interesting interactions. And so it shouldn't be the case that these additive ensembles should work in that case. But it's a little bit more ambiguous for other cases. So in popularity prediction, maybe you can actually just look at the image, train a model just based on the image, then look at the text, train a model just based on the text, and then add those predictions together. So the line's sort of fuzzy. And what people do generally, including us, is they compare models with differing expressivity. So maybe they'll, train an ensemble-based model and compare it to the performance of like, a 10-layer neural net that does like 1% better or something, and then claim that it's the model interactions that really matter. So, okay, sure. The other sort of model that we're interested in are multimodally interactive models. So these are the class of models that can look at visual textual interactions, and they're defined by exclusion. So interactive models simply cannot be decomposed as these additive ensembles. And so this is something like a neural network with multiple layers. This is something, there's all sorts of models of this flavor. One that we used in the paper, which is kind of a throwback, is a polynomial kernel SVM. Really bringing it back to 2005 or something. But nonetheless, it's, you know, a performant model that cannot be decomposed in this additive fashion. So the skeptics among us might be, you know, furrowing our eyebrows a little bit and thinking, is it really the case that additive models are fundamentally less expressive than interactive models? So going back to these equations, like maybe it really is all you need to do visual question answering to look at this, you know, additive ensemble. I've sort of hand waved a bit and said, you need more than that. Is that really the case? It turns out, yes, it really is the case. Additive models, you know, in theory, just shouldn't be sufficient for some tasks. And in the paper, we explore this in a toy setting. The idea is that we're going to express our text and our image in terms of binary indicator vectors. Again, this is just a toy setting. These don't actually correspond to images and text, but it's just for illustrative purposes. And we're going to assume, you know, this binary input. Then we're going to sample a random logical function among the set of all possible logical functions that have 6 Boolean inputs. And then we're going to see if an additive model can fit this, you know, one that just looks at the t variables, one that, and separately just looks at the v variables and adds the resulting predictions together, or if you really actually do need, you know, feature interactions to do well at this task. And it turns out for non-trivially sized models in this, or non-trivially sized problems in this toy setting, you really do need more than additive models. So I won't get in too much in the details here, but the blue and the the orange and the green line just behind it represent the performance on just fitting the training data. So this isn't even about generalization. This is just how well can you fit this random function. These lines are the performance of additive models as you increase the number of variables in your problem. And in contrast, the purple blue line is the ability of an interactive model, one that can fit these interactions. You can see that it gets 100% accuracy for all of our tasks, whereas the performance of the additive models decreases as the problem space gets more interesting. And I want to emphasize that, like, this is a toy setting, but it shows that even like trivial logical functions of like 10 variables can't be fit by additive models perfectly. Like you can't even fit them really. And so this suggests, at least to me, and that, you know, we're going to need something better than additive models to do most real cross-modal reasoning problems. Like if we want to actually be doing cross-modal reasoning, we can't get away with just doing additive. As a touch point for the number of variables in a less toy setting, if you think about visual question answering, like if you want to be able to ask about the counts of any individual object in an image, like there's going to be at least 1,000 types of objects, let's say, or like 100 even types of objects. And you want to be like, how many cups are there on the table? You're going to need a separate variable for each, you know, like type of object. So we need to have the number of cups, we need to have the number of bowls, and so on. And given that you need at least one variable on your image representation side to track the number of counts, we think that 10 variable problems are, you know, just very small relative to, you know, the actual complexity of the logical inferences we need to be making in practice. And so overall, the argument here is that you shouldn't be able to do that well on very complex inference tasks using additive models. Good. So how do we actually use this in practice? So I've been discussing this sort of toy setting where I'm talking about binary variables. I've been talking about fitting the training set. In practice, no one really is thinking about this sort of problem. And what we really want are tools that we can use to improve our model comparisons for actual tasks. And, you know, this isn't quite as simple as model comparison. So if you trained a less expressive model and simply compared its performance to a more expressive model like LXMERT, that wouldn't necessarily be sufficient because it's quite difficult to tell what the heck LXMERT and others are actually doing. So a little bit of detail about LXMERT. I love this model, very cool stuff. The idea here, you know, it's very complicated. There's an image and some text, and the image is first, you run an object detector. So you get 36 bounding boxes, and then for each of those bounding boxes, you get a few hundred dimensional feature vector. Then there's some, self-attention transformer encoding. That's just the image side. On the text side, you do self-attention over the tokens. And then once you do all of this self-attention, there's, 9 more layers of processing. All of this is pre-trained on different tasks. Basically, the case I'm trying to make isn't that LXMERT is good or bad. I think it's very good. I think you should use it. But the case I am trying to make is that this is a really complicated model. It's really hard to tell if this is actually doing, cross-modal reasoning, or if it's, maybe doing something more similar to additive ensembling, which, as we've discussed, is not sufficient for many tasks, or it shouldn't be at least. Good. So what can we do here? Well, in this paper, we introduced this method of projecting models down to the space of multimodally additive models. So in the right here, we have this bubble, the set of all functions that can decompose in this additive fashion. Again, these are not that expressive. It turns out that you can actually take the predictions of arbitrary black box models, maybe it's LXMERT, maybe it's a polynomial SVM, maybe it's a neural net, and you can actually compute the optimal projection of these models down onto this less expressive space. We prove that such a projection not only is possible, but also is unique and optimal. So you really can just find like the best multimodally additive model that approximates these more complicated models. And the core of what we're going to be doing here is we're going to be comparing the performance of these projected versions of the models to their original ones. The argument being, if the projected versions significantly underperform relative to the full versions, then we can be a little more confident that we're actually doing some interesting modeling of visual textual interactions. In contrast, if these projections work about as well as the original models, then like perhaps these image text interactions that we kind of hope we're modeling are not actually being incorporated for predictive gain. So that's going to be the argument structure here. I can talk a little bit about how this projection works. It turns out it's sort of a relatively straightforward adaptation of some statistical machinery from like, older school statistics, not deep learning. You basically take your image text pairs in your development set, you run them through your model in all possible combinations. So you only observe certain pairs, so images with certain captions. But in this framework, you're going to evaluate all possible pairs, and then you're going to take an average for each image and an average for each caption. And these represent the potentials for each image. So maybe, okay, I guess as a touch point, consider the popularity prediction task where we have images and captions. What you do is you take the image that was posted to Reddit and you evaluate the model's prediction for its true caption, but also for every caption that wasn't posted with it. And you take the predictions for all of these things and then you just average out. So you get an average prediction score for that image. And you do this for each image and also for each caption. And it turns out this corresponds to a projection process. And there's a proof in the paper and a little bit more formalization of how this works, but it's a pretty simple computational process. And so it gets you the best possible additive reconstruction of your full model. Good, so let's look at the experimentation a little bit. So we looked at these 7 tasks. They vary in size, they vary from the source that they were constructed. I won't get into the details here, but they're all very cool tasks, I think. I should emphasize that our goal here isn't to downplay the efficacy or importance of any task. We think these tasks are very important and may very well require, cross-modal reasoning. Like humans, when they're doing this task, might perform interesting cross-modal inferences. Our goal is just to develop model diagnostics that tell us if the models are working how we work, if that makes sense. Good, so here I have switched the tasks to the columns. Each of these tasks has an evaluation metric associated with it and different cross-val setups. The previous state-of-the-art models performance is given here. Good. So if you take some off-the-shelf feature extractors in 2020 and just train a linear model on top of them, it turns out linear models are additive. So they're not they can't do cross-modal reasoning. You can see that you actually set a new state-of-the-art in all of these data sets. And this isn't something really smart that we're doing. This is just like, it turns out that the models these days, like Roberta is better than Unigrams. So here you go. This is just to set a baseline for comparison, not to like brag about how, we get state-of-the-art. Good, so linear model does pretty well, and it's additive. In contrast, if you train models like LXMERT, which are capable of modeling cross-modal interactions, you get this number. So you can see that in all of the cases, there's a little performance boost when you add in this additional model capacity. And most studies, probably including our own, would end here arguing that it must be something about the interaction component of this model that is leading to these performance gains. But using our new tool of empirical projection, we can actually audit that claim more directly. And you can see that if we take these predictions and project them down to this less expressive space, we're still doing incredibly well. In most cases, like, we're not actually losing any performance. We have one case where we do, which is sort of hopeful. But for at least 6 of these tasks, like, we're not really losing that much performance. Sometimes we even gain performance. And so what does this say? This says that the model we were training, that was this interactive model, LXMERT in a lot of cases, it wasn't doing the thing that we thought it was doing. We thought it might have been doing some interesting cross-modal reasoning, but in actuality, the models really seem to be just doing additive reasoning, but disguised in this very, expressive model. Again, this isn't always the case. So in TViz, it looks like our model for 3 F1 points worth of data points is actually utilizing interactions to do better. So there is some hope. But we think this EMAP tool is a really important tool because it can illustrate what our models are doing better than just doing model comparison. It turns out too that visual question answering data sets, which are often very carefully balanced to avoid this problem of single models, single modal models outperforming unimodal models. People have done a ton of work in visual question answering, making sure that you can't solve these tasks just by looking at the text, for example. It turns out these sorts of data sets that are well balanced don't have this property. So if you take a state-of-the-art model and then compute the projection of it for these well-balanced tasks, you get a huge performance drop. And so it isn't that the models are incapable of learning interactions. It's simply that the data sets might be too simple statistically for the models to require learning them. Like, it might be the case that we either need significantly more data to make interactions worth learning from a statistical perspective, or if we really want to learn interactions, we might require ourselves to construct more well-balanced data sets that sort of force cross-modal interactions to be learned. So overall, the takeaway isn't to stop doing these studies. I think they're very cool, and I hope to do more of them in the future because I think studying how we communicate online is really interesting. Back at the beginning of my PhD, I wasn't really a machine learning person. I was studying, online communities, and so I have an intrinsic interest in this. I think it's quite interesting communication. I think psychology is very cool. Keep doing these studies, but if you're going to do these studies, do report the performance of the multimodally additive projection, because it tests an important hypothesis that we might be not testing as well as we could going forward. And hopefully people start adopting this strategy. It can be implemented in like 10 lines of code. We think it's really worthwhile. And yeah, that's kind of the big takeaway from this work. And with that, I'd like to thank everyone for virtually attending this talk. Again, I'm really sorry that I couldn't be there with you today to share in person, but I think that I can certainly take questions offline, and hopefully I can maybe have a more interactive piece of this talk with folks going forward. And so, yeah, thank you for watching, and definitely get in contact. And I'd love to hear if you have any questions or thoughts or comments. Yeah, thanks so much.